So I wanted to take this opportunity to make a brief comment about Maury's talk. Showed a wonderful picture of Chris Quigg in the earlier information. At that time, we were all very excited about the SSC. Chris was very involved in it. I was pretty involved at Berkeley, and we decided this was so exciting, we really should write a book about physics in the SSC, but it was important to get it done before the SSC was finished. We succeeded. The book came out this week.
That's great.
So we theorists are always looking for failures of the standard model, and we have been faced as right in front of us for many years. Really. So we're going to hear about that possible violation of the standard model in G-2.
Thanks.
Dave Hertzog.
First of all, it's a real honor to be invited to this symposium and to listen all day long to very important physics from the past and things I don't do. A lot of you are experts in different things, and I've been involved in these kind of muon experiments for about 30 years, and before that, some other things with antiprotons. So this may be a little bit different, but I hope you enjoy it a little bit. And when I was trying to, this is not at all like a normal G-2 talk I would give. I'm not going to tell you the details of why you would believe our analysis down to the last tiny little bit. You'll be so bored. The brownies will kick in. You'll be sound asleep. So Giorgio asked me to actually reach back maybe a little bit to a time period, which I didn't realize, of course, before I was involved in anything, in which actually Stanley was involved in a G-2 experiment. It seemed to be a little bit of a hobby for a sabbatical or so. And it was an extremely important one of the G-2 experiments that I'll get to. But then I thought, well, why stop there? So despite the title, which I used because you told me the title to use, I'm going to go back even further. But to set the scale, to set the reason that probably you even include me into this thing, there's been a real buzz around the idea of G-2 measurements, and this is sort of the latest thing where there's been three pretty good measurements right now. There's the Brookhaven measurement that was completed about 20 years ago or so, and it's been sitting there for a long, long time. And then 2 years ago, the Fermilab experiment released the first 6% of its data, and rather euphorically, it landed right about at the same number. And about 2 months ago or so, we opened up the next batch of data, and that landed so close here, we didn't need to redraw the plot, which was really disappointing in a weird way, but sort of nice. And so the world average is this tiny number here, in which is measured to about 200 parts per billion. This is the muon anomalous magnetic moment, or G-2. So keep the number 200 parts per billion in mind, because I'm going to talk to you about a little bit of history, so you'll see what was before 200 parts per billion. Well, then what do you do with that number? You compare it to the standard model. In 2020, the world's theorists had published a rather thick volume where they had considered all of the contributions in the loop physics and so on. And when you look at that right now, that looks pretty awesome, right? And if you did the math on that, then maybe nature's nice again, right? But it looks pretty good. But none of us threw our hands up like that despite seeing that, because in fact, over the last 2 years, a lot of the theory got kind of muddled again. And so I'm going to tell you this story. Okay, so that's the beginning. I like to tell you the end before the beginning, and then you know where the story is going to go, and I'll tell you why those pieces ended up where they did. So this is really old, right? This gets back to, I would say around the time of my birth and so on. But I love this paper, and in classes that I teach, I often include reading this paper by Li and Yang, but then in these follow-up papers. And it was really, back to your kaon physics thing, so it was really a radical thought to think about the idea of parity violation in the weak interactions. And in that paper, there's recipes of the experiments you would want to do, one of which was the Madame Wu experiment, and then the one that's a little closer to my story today, it involves muons, and there's another ones for hyperons and so on. And then rather rapidly after that paper, Garwin, Lederman, and Weinrich did, they just had to almost reconfigure a simple experiment at the Nevis lab. You can do this relatively straightforwardly, but it tells you that parity violation tells you that when the pion decays to a muon, that muon is going to be spin polarized. And when that muon decays to its electron and neutrinos, it's its own polarimeter. It actually is doing it. And so that's the ticket in which if you put a muon, a spinning muon in a magnet, basically it's going to rotate around like that. And it's so easy to do that I actually built an experiment like that. It's still running at the University of Illinois, that we do that with cosmic rays for the students. We drop muons in, catch them in copper, rotate them in a magnetic field, and we get data that looks just as good as that. That is 50 years too late. We didn't get any credit for it. Let's go back a little earlier. I'm talking about muons, but you can do all of this stuff with electrons, and muons are more sensitive to new physics by about a factor of 44,000 than an electron. We'll leave it at that unless you ask questions. The idea of chasing down the G factor, and it's supposed to be exactly equal to 2 in these days, and realizing in atomic physics experiments and so on, it was starting to show the tiny little deviations of G from 2, from quantum effects. And so this whole industry began with ushering in basically quantum electrodynamics. And they're all Feynman diagrams now, and students who take quantum field theory can take these kind of hieroglyphic diagrams and calculate them depending on how well they do. But the first calculation was really Schwinger, and if you look at this in expansions of alpha over pi, you get this number which is a half. And it was so important that he put it on his gravestone, which I find it kind of interesting to end up there. These days, people know these diagrams, 12,500 of these diagrams involving quantum electrodynamics with these complicated little diagrams. It's so well that it's extremely far beyond any measurement level that we're dealing with. So you can forget QED. And actually, in addition to that, that's a little review of that. You can actually say, well, anything that couples to the muon that in a quantum way that would make a little fluctuation could affect the magnetic moment. And so you could actually, remembering the electroweak theory, so you could change this little sort of first order Schwinger term. You could just put a Z in there and you can calculate that. And these things represent a kind of a couple part per million level deviation from the thing. So part of the idea of the Brookhaven experiment actually was, could we see that diagram? Actually, could that diagram? That was before people heard the word like supersymmetry all over the place and so on. But then there's this other problem called, for vacuum polarization, you think of vacuum polarization, it's standard, you would imagine E plus, E minus, and that was included in everything I mentioned earlier. But you could also have it with that vector there, or that photon, you could have pi plus, pi minus, or any other thing that would combine like that. And now you have a hadronic blob, and you cannot calculate that thing with any perturbative methods. So that has to come along in a different sort of a way, which I will have to mention, because that will be the problem. That will be the thing, the thorn in the side of this entire story. So just keep that little diagram in mind. And this is the book I was referring to. It's a lovely read if you have a few weeks. But in the end of the day, the theory calculation is known to about 370 part per billion, according to this. And that the entire uncertainty is really driven by, these days, more or less this diagram. So I should just mention how this diagram is classically determined. And I hate to always say it's the theory diagram, and look at the theorist and go, it's your fault, because in fact, this is mostly just experiments like Babar and other experiments. And so what they do for that is imagine this diagram again, you see that thing. And if you came along with a pair of scissors here and you snipped it down the middle like that, cut it right in half. I know I'm looking over there because that's the only thing I can see. I suppose it's here as well and there. Sorry, I should look at you guys sometimes too. But anyway, then I'll go like that. Anyway, if you snip that diagram in half, then you have this little tadpole thing. Here's the little yellow photon, and there's the pi plus, pi minus connected to it like that. And so that's the piece of the diagram you'd kind of like to have, right? It's symmetric. And you say, how can I make that in a clean way? Well, I can bash in a positron and electron together, and E plus, E minus goes to hadrons. And then there's a dispersion relation, which is written at the bottom of this slide. We don't need to talk about that much, but that's a formula that had been known for a very, very long time. It's a very straightforward idea to get this crank. And all of these beautiful colored picture here represents, a few years ago, the world's compilation of E plus, E minus to hadrons over E plus, E minus to muons, which goes into that integral. And that's really, if you know that well, and it comes from all of the experiments that do that, E plus, E minus, and there are 4, 5, 6 experiments in the world, then you get this number. to the extent that they did their experiments accurately and gave full cross sections. So the takeaway there is that this is what dominates the standard model. Okay, just to back up one step, if people don't know why am I talking about G-2? What is G-2? Well, G is a really long number. And if you want us to measure G, that's even harder by about a factor of 800. In fact, what we're interested in here is just the digits down here. And so when I talk about 200 parts per billion, it's just on these digits. I could exaggerate our experiment by telling you what the uncertainty is compared to that thing. But the idea is to design an experiment that is sensitive to that difference, not sensitive to G, like it was when you saw the Darwin experiment like that. These experiments are going to be sensitive to the difference of G from 2. That's therefore the name. And the way you get into that, the fundamental principle of these experiments then involves the idea that you put this muon in flight in a magnet so that it goes around. And then you have this little pictures here, which are kind of, oh, there we go again. Oh, there we go. And we have these two arrows. The blue arrow is, the red arrow is just the momentum vector as you see it go around. And the blue arrow here is the spin direction. And there's a couple of relativist expressions here for the cyclotron frequency, that's it going around in a circle, and the spin frequency, that's it going around in a circle. And you can see they look a little bit funky different. But if you just do the subtraction between the two, the marvelous thing about this is the gamma factor, the speed drops out entirely. And you end up with this very simple expression here that the difference frequency between the spin vector and the momentum vector is proportional to the anomalous magnetic moment. So if you can measure this difference frequency and if you measure the magnetic field, then you get the anomalous moment. So it's a simple recipe, and that allows you to get the kind of precision. If it wasn't for that, you'd be dead. None of us could put in a beam and know the momentum to, part in a million or something for anything. Okay, so going back with this recognition, in history, then there were three experiments at CERN. Francis Farley and Picasso and others were involved in these for years. The first one was like, how do you do that? What do you do in the 1960s for that, 65? Well, they got this long solenoid. They brought some muons in a way. They spun around like this in a clever way of using the magnetic field out the other end of the door. And they basically got this kind of this detail, like that. But you can see the level compared to 200 part per billion where we are, we're nowhere close, but it's a good start. And then they thought, okay, it'd be better if we put these in a ring, we can keep them longer, but how do you put them in a ring? So they made this little tiny ring. They didn't know about certain things I'll tell you in a moment, but so they brought a proton beam right into the ring, smashed it, it makes some pions. Those pions might have decayed, made it, it's a really inefficient mess, and it lit up the place with radiation like you would believe. But in the end of the day, they got some wiggles here. That's the deal. And now they're down to 265,000 parts per billion. The next level though is realizing the CERN-3 experiment. And this is the one that Stanley was on, I guess, during his sabbatical year or so. And this had really, I think, super breakthrough ideas. And the idea here is that, well, once they're in a ring, you have to keep them there. You guys, if you put a charged particle in a nice uniform magnet, it's going to go around if it was dead level, but if there's any kind of up and down pitch to it, it's gone like that, which we would immediately tell our freshmen when we talk about that. So you need something to keep vertical focusing. They're going to go around in a circle. And so what do? You can't put another magnetic field in there because you have to know the magnetic field really, really well. So you put in an electric field, you put in a quadrupole. So you make a penning trap out of that thing. So that means if you put an electric field in there, now you have another thing. Now the muons are zooming through an electric field, and you have to think about that. So the expression that I showed you, which was relatively simple, has now a couple of extra pieces to it. And those pieces involve the fact that, well, it's going to oscillate a little bit like this, and that means it's not always going to be going perpendicular to the field, and that's called the pitch correction. And that was well understood by these CERN guys. They wrote papers on exactly the formulas of which one would have to correct this thing. There's non-trivial corrections that they have to make for that. But then the next one you see has some interesting terms in it. You see that this beta cross E, that beta is that speed vector going through the electric field. You have a charged particle through an electric field. It's a motional magnetic field to the charged particle. It means it turns its spin. But the coefficient out front of it has this an almost muon magnetic moment minus this thing that looks like kinematics with a gamma. And in fact, the nice thing about that they discovered for that CERN experiment was there's a value of gamma, that means a momentum, in which that term cancels exactly to zero. And that was the recipe that's been followed by CERN, by Brookhaven, by Fermilab, and that's the way you would do it because it's so good. It still means there's a big correction after that because you could be a teeny bit off of that momentum and it's a big correction. It goes very rapidly. Okay, so the summary of the CERN experiment, the CERN-3 experiment, is they got down to 7,000 parts per billion. That's pretty good. They pushed the tests of QED. These are all really successfully tests of the correctness of QED for a long time here, out to what they called sixth order then. They saw the hadronic term for the first time. That's a pretty big term. The hadronic term is 68 parts per billion per million. And they had these wiggles that you see here. And this is the authors of the paper that I thought I just mentioned because you see Stanley's name right there. These are rather formidable people, by the way. They're not long list of names here. And I know most of them just because of their significant contributions to this effort. So what about this problem? The problem with the CERN experiment, the only one, is statistics at some level. At some point, the way the muons were born or stored in that ring was to bring in a pretty intense pion beam. This is an ugly thing. You bring in a pion beam into the ring, and a pion at that relativistic boost that it has to have for that lives a fair amount of time. In fact, it lives such that its decay length is 175 meters, and the ring isn't anywhere near that. So the chance that the pion comes in there and starts to go around the corner and then accidentally decays in the first 100 nanoseconds and then accidentally throws one of the muon onto the orbit is so inefficient, it's about 25 parts per million chance. So you can imagine it just blew up with background, and then when the dust settles, there's some muons running around. That leads to the next experimental idea. So at Brookhaven, the idea was, hey, that recipe from CERN's pretty good. What would be the next step? The next step would be to bring the muons in directly and quietly and cleanly in a way. And so that involved inventing the idea of a very, very fast kicking magnet. Because, or let me remind you of what happens when a particle goes, you have to bring the beam in through some kind of a corridor here that's offset to the circle you'd want, because in a uniform field, everybody knows a charged particle is going to go around in a perfect circle and it would whack the front door of this that it just came through if you didn't bump it. So 90 degrees around the ring, right here is the ideal time to give it an outward kick like that, which then lands it on the orbit so that it goes around in this centered orbit that's blue in this picture. Well, the beam itself has a kind of a width like that, maybe 50 nanoseconds or 60. To go around the ring is 150 nanoseconds. That means you've got to give it a whack and then turn the thing off. That doesn't happen. Nobody knows how to build that thing yet. So in fact, you end up with a kind of an ugly way of doing it. These things are the beam, these blue things, and this red thing is sort of what we called the kicker. But it sort of worked. It worked pretty well. And so with that, that's the way we ran the experiment for a number of years at Brookhaven. And now we're down to 540 parts per billion. So it's a big step, again, another factor of 15 or whatever beyond what CERN was. But again, there's a limitation. You look at that thing, there's a limitation. And the limitation was at Brookhaven, the place where those pions were born was about 100 meters away from the ring. And so what really came through the door wasn't muons, but was pions. We had to do all kinds of tricks to limit the number of pions, but still they came into the magnet. They did their thing by smashing into detectors and steel. And all of this baseline right here is from neutrons. We heard about neutrons earlier. We had tons of things to deal with thermalized neutrons who ran around and lit up the detectors. So there was a bit of a, from a certain point of view, as the guy that built all the detectors, I was getting hammered by this background. And but it still worked, but it's something to keep the eye on it that would ultimately limit the experiment. So that at 540 parts per billion precision, this was the Brookhaven final number around 2004. And this is the state of the standard model theory. It was certain things were bouncing around as people went through terms that are beyond the hadronic vacuum polarization. And so there were no new measurements in here, but so around this time, 2009, I kept thinking, Vernon Hughes and Lee Roberts were sort of in charge of that experiment originally. We lost Vernon before we had the final number. But he says, what would Vernon have done in this thing? We just lived there in purgatory, 2.5 sigma, 3 sigma. And so we thought, we really have to resolve this for the community by coming up with another method, another experiment. So there was nothing limiting in a certain way, fundamentally getting to the higher level of precision. If you go through the proposal very carefully and look, where is the showstoppers and so on, you can do a better thing. And after searching around in Japan and at Brookhaven and Fermilab, we eventually realized we could do something rather wonderful if we got to move the experiment there. And so this is a group of us actually on the campus at the University of Washington. We meet here and there in different places. But the thing is, to put an experiment together that requires what I'll show you in a few minutes, to make an experiment like this, you need experts in all of these communities, from particle, nuclear physics, atomic, optical, accelerator, and theorists. We actually have a collaboration which is actually quite as broad as that. These represent homes, funding sources, different things like that, and it's extremely interesting to do it this way. So the way the beam is done at Fermilab is very nice. So basically, you start with these HEV booster protons, you run them around that recycler, you use some RF to break them into these ugly looking things, but that's the best they could do for us. These ugly things are about 120 or so nanoseconds long. One by one, they bash into what used to be the target that made the antiprotons, if you guys remember the antiproton system. And then from there, they go into what used to be called the antiproton accumulator 4 times. This is, they go around backwards like that into this thing we now call the delivery ring. The pions are now so tired of this activity that they are completely gone. They're like down by 10 to the -5. And the muons are just like, they're running around just fine. And eventually we put a rather pure muon beam into the ring. And it's a huge difference. And it's much more frequent per second. So we like that. And that's been a big deal. So here's a picture of that ring. It is the same magnet actually as the one at Brookhaven. There's a long story how it got moved and what we did with it. But anyway, the muons are going to come in here through this superconducting inflector, which is a field-free region in the back of that iron yoke. They're going to get through this 90 degrees. They're going to see those plates right there. We're going to pop a magnetic field on and off with a really sharp pulse, bang, bang, to give them that outward kick. Then all around the ring are these electric quadrupoles. You see these plates sitting like that in about 40% of the locations around the ring. That gives the vertical focusing like that, which is part of the reason that you get basically the beam motions that happen. So the betatron motions are, you can see this is an actual using straw chambers. This is all updated instrumentation. We never had this kind of look before. We can just see where those muons are. We know these frequencies. We know if they're stored. And we need to know where they are because we need to integrate the magnetic field that every muon has seen on average. That's what goes in the denominator. So then the detector system, again, I made these this time as well. This is a different thing, much faster. Basically, these things are little calorimeters that are located all around the ring like that. When the muon decays, the positron curls in to hit one of these detectors, in which case they're all made out of nice glass crystals, the Trinkoff crystals, to be very fast. They make a signal that's no more than about 7 nanoseconds like that. It's digitized. And this is the ticket. Why? What you really see is the energy oscillation that these detectors see back and forth as the muon spin goes around. So the vectors that are moving around there represent the spin vector in blue and the red vector in the now watch when they're lined up. There's a lot of high energy events. When they're backwards, there's low. That's just a parity violation. And so all you have to do is say begin run. Begin run happens. You start to collect those events that are above the threshold, and you immediately, literally within minutes, you're getting a plot that looks like this. Now you just rinse and repeat and do that for years. The magnet had to be really as uniform or better than the precession frequency. You don't want to do all that work and then have your uncertainty be based on how well you know the field. But the magnet that Gordon Danby at Brookhaven designed was incredible and had all kinds of tools and so on to work with it. And we basically brought it, put it back together again. And the trick that I want to show you here, and I hope this works, because I don't know, maybe I'll do it this way, is we got, after a year of work, we got it basically to the uniformity that we left at Brookhaven, but not better. And to get it better, we had to iron out these little tiny micro fluctuations, which you can see happening here. This is 0 to 360 degrees right now around the ring. We're mapping it with a trolley, and we're building with 8,000 tiny pieces of iron that we cut in a laser in our lab, little plates that inverted basically the magnetism poles in a way to smooth it out. And the end of the day, it ended up being about three times more uniform, which we needed in our systematic error budget. And then this picture you'll see in a moment, because this is kind of fun, but basically when we ride around, we have this trolley. This trolley has NMR probes on it, and every 2 or 3 days, it drives around inside the vacuum with these NMR probes on the front of it, and it makes these free induction decays from the proton pulsed NMR. So when you see a nice smooth thing like that, you're in a uniform gradient piece of the field, and so we're able to map that field out, and that's what you're seeing here. As this is going, this is just going around the ring, so the dot is telling us where we are as we go around, and that we know the integrated field way better, to about 50 part per billion in the end of the day. There are 5 miracles, maybe more, that allow a measurement at this precision. And you have to think nature, at least, Giorgio, is kind to make the measurement. And this is what I like to list. The muons are polarized naturally from 97% from pion decay. The precession is proportional to G-2 and not G. The magic momentum allows you to store the beam without perturbing that precession. The parity violation allows you to analyze, on average, the spin direction of the muon when it decays, and the pulse proton NMR magnetometers allow you to make individual measurements of field to literally 10 part per billion and better each probe, and then average it all with a lot of work. Now, of course, what we do is we measure the field and the precession frequency, these two things. But to get the anomalous magnetic moment, you actually have to rely on these other constants, of which they're listed here. They're basically ratios electron to proton magnetic moments and masses, the GE, the electron factor here, and so on. But these are at this point known well enough that we don't matter. Those same things operate if we look at how you would analyze the data. This is actually the kind of formula that I wrote that we do. Essentially, this is that precession frequency divided by the field. And so when you really look at that, what you're seeing here is the things that are involved with many, how we distribute, how those many people with the different talents end up. We have a blinded clock. We have the raw percent. That's the wiggle you would fit if you saw that thing. There's electric field correction when you're not quite at the magic momentum. There's a pitch correction for going like this. There's a muon loss correction. There's a very complicated phase acceptance. If you have another hour, I can explain that one. There's magnetic field calibrations, there's field trackings, muon weighted, and then there's transients. The thing about life about transients is it's a very delicate thing. If you pulse something like you pulse the quads on, you get a little jiggle like that, and you get a perturbation in the field, and we have to map all of those things and know what they are. But essentially, in the end of the day, the numerator is just an accurate measurement of this, and the denominator is an accurate measurement of these two pictures together. This is the uniformity of the field in the mapping here, and then the density here is where the muons have been living in that field. It's the convolution of those two. So when you do all that, it's all blind. The clocks are blind. They're done by different people. Then you're doing COVID, because this is your answer. The entire analysis was done during COVID, so we were all at home happily doing that. And then we have to vote, and the way this works, that we all vote. We open up envelope 1, we open up envelope 2. These are the secret codes that tell us the frequencies that our clocks have been running at for the last couple of years. We find them the same numbers, type in something in a spreadsheet, and that's how we got the number. And that's how we got to that thing. And it was really exciting in 2021 because after a very, very long time, we realized that especially the handful of us that were left from the Brookhaven experiment, we realized that we didn't mess up, it seemed like, because by now we thought we must have messed up. And so the combination between Brookhaven and Fermilab looked kind of interesting. Now, the aftermath of all of that, in the near and the far future, I'm going to flash these 4 kind of icons for a moment for you. I haven't kept track of my time. I hope it's okay. I'll just tell you anyway. So it used to be that I could rattle off to you all of these different things about what beyond the standard model physics it was. I was a big fan for a while. This is before we took the measurements. I was excited about supersymmetry and lots of stuff like that. But then, you know what happened while we were building this experiment? This LHC thing came along and it was crushing a lot of the, where's the TeV physics and all that we were like supposed to be drowned with states and so on, and it's not there. But there are things that sneak around, okay? You can still in quarters of supersymmetry space and these models, there are little places, but generally speaking, when the theorists evaluate like what could make that difference for G-2, they have to like super fine tune, and they don't like the parameters that they chose. I don't know what like means, but they don't like them. And so it's kind of uncomfortable, let's just say. So that's, so I'm not too excited. Then other people say, well, what if the standard model is wrong? Okay. And so around the same time that we released the first result in 2021, at the very same time, Nature published the first precision calculation using the lattice only, just the lattice, by one of the teams of many lattice teams. They claimed an uncertainty like this. They're called the BMW collaboration. And they say, hey, this green box should be really over here. If it's over here, well, you can imagine what that means. Okay, it gets worse. You already looked at this slide. Let's stay with it. Then in February of this year, the Novosibirsk experiment CMD3, there's a CMD3 and there's another one there, that runs called SND2K. They run on a different way of using E+, E-. They scan through the resonances. They released a result which on its own would be here, where all the other experiments, so there's Babar, Chloe, SND, their previous version of themselves called CMD2, Clio, everybody else is over here. And they released the result, which is here. So they have been scrutinized, interrogated, tortured, and everything they've done is held up. Let's just say people have tried very, very hard. It looks like an excellent analysis. They have answered every question by anyone, and it sits there. So if you threw away 20 years of everybody else, because you guys were all wrong who did these experiments, only these guys are right, then that would actually stick the number way over here. And so eek, that's starting to look not so cool, right? Okay, then it's our turn again. So we have actually completed the experiment since that thing, and we have actually, I like the fact that this is the second experiment in a row in which I've been involved, which got exactly or more than the proposal amount of data and precision. And we asked for 21 times the data, and we got 21 or more than that. And when we've gone through our uncertainty budgets, we are going to beat our proposal goal probably of 140 parts per billion. So this is the first paper that you saw, and the second one is here now. It's published in PRL a couple weeks ago, and that's based on this. And so we still have 75% of the data to go, and this is cranking its way. There's a lot of data. There's many petabytes of data, this stuff. And so we're back to the story at the beginning. This time I won't bore you with the kids smashing their heads. What happened to this? Goes back. Oh, backwards. Backwards is this way. There we go. Yeah. So we're back to that same thing with this ebb and flow of the chess game. And I was thinking, gosh, I just wish I had a nice, crisp conclusion for myself, for you, and everything on that. But when I think about it, I think a physicist like Stanley, from what I've learned and studied, would really enjoy this idea of the ebb and flow. He would enjoy the technical aspects of this kind of experiment, what's involved in doing it. The road is long, it's bumpy, hard, and so on. The only thing in our collaboration we can do is make sure we do our part of it right. That's the best thing, is just hunker down and not get seduced by theory. But there is absolutely a lot of data coming on hadronic vacuum polarization, both in data, new data, a lot of new data, and a lot of very sophisticated lattice calculations. So in of the order of the 2 years it's going to take us to get this final result out anyway, we fully expect that the theory will also tell us what we're aiming at. And with that, I'd like to thank you for your attention.
All right, we have some questions.
Georgia.
So Dave, I'm just curious, I never occurred to me, it's magic momentum.
Yeah.
You don't hit it right, you don't necessarily have, so how far are you from?
No, we hit it right. It's just, it's parabolic around that, it's parabolic around the magic momentum. And so if we store plus or minus about 0.2% in delta P over P around the central value. And that little bit introduces of the order of a 400 parts per billion shift. It's a non-trivial shift because it's larger than our uncertainties now.
So are you advocating E plus E minus measurements?
Of course. Absolutely. Bell is very important what Bell's doing. The Babar guys have a huge important data set that they're working on right now. Chloe people have 7 times as much data that they've never analyzed, and they're now setting up a double-blind version of that. Radiative corrections are really important in that. There's a paper out floating around by Babar right now about that, finding the Fakara and the different generators that have to be, look like they're not quite right, and it may have affected a difference between Chloe and Babar. And we'll see. S&D hasn't published the equivalent data from the data runs that CMD3 did. They took data at the same time, and they haven't released that yet. So we'll see what they come up with.
Is there anything special about the CMD experiment that's different from all the others?
No, they compared to their previous experiment, they upgraded in ways that I sort of thought, okay, wait, that struck something to me, but they've answered all those questions. There is a big fundamental difference that Babar, Bell, Chloe use this technique of radiative return. So the first thing is, they sit at a fixed energy with a center mass, E plus, E minus, and a gamma goes off, and that I call it downshift, whatever, downshifts the collision energy to the sweep. So that's so that piece of radiative physics has to be done right off the bat. And then on the left, these guys tune the beam, click, 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 they're moving the energies up and down. So they're mapping it out like that in formation. That's important to see if they overlap. Yeah.
More questions.
When you were shimming your magnets,
Yeah.
and are you sensitive to any environmental effects? Like, I always remember like lab was to the TGV schedule.
Yeah. No. I think we do have environmental magnetometers out. We were worried not about the TGV, but we were about our trucks, and we were also worried about something more synchronous, which is when the cycles of the machine you saw there that brought the muons in, you could imagine the ramping and unramping of various magnets. So we actually mapped out very carefully the footprint of those magnetic resonance before we even stuck the thing down there. And then we have those things in a wall. But you're kind of inside this thing. You're at 1.45 Tesla, and you're inside this kind of shielded thing as well, the yoke of the magnet. I heard
I have a question. I was under the impression that in addition to the vacuum polarization diagram that you drew, there are other corrections where you have 2 photons in.
the hadronic light by light.
Yeah.
I didn't mention that. I didn't want to go quite down that street. There's been a lot of extremely good work with that. Now, for a long time, that's a higher order diagram, everybody. You can't, normally you couldn't get that by data. And so there were all these like funky little small hadronic models, and they kind of converged in a certain way, but they didn't all have the same terms. They all were
about how big are those?
it's it's in these units that is kind of 110 in this AMU unit 10 to the minus 11. And the thing is, since then, 2 things have happened. One is the Lattice got that with the campaign that started earlier at the same level, almost, they don't have to do it Lattice doesn't have to do it at 0.5%, has to do it at 20%, and they've done the same. And secondly, people have developed a dispersive technique to use data, and so that thing has come out in almost each one of the channels has been dead on to the individual channels that consist that. So that's first of all calmed down, have been affirmed, and its error is going down. So you're correct. That was about 1/3 of the problem. Yeah.
Any more questions? Yeah, Michael.
Yeah, I wanted to ask again about this experimental determination of the hadronic vacuum pose.
Sure.
So this is like a 2% effect in the acceptance of your detectors. And I must say, for me, that seems extremely ambitious even to get to that level. Maybe for Babar, you've got 1% in central events, but as you say, these are often boosted events. I wonder if you have any more comments on this about how,
You're saying a collaboration delivers an R ratio
yes,
of some channel, pi.
right. And
So
this
they're
has
doing
to be
pi to
precision.
mu. And they're saying, hey, we're doing that to 0.5% precision.
Yeah.
Right. I think there are people in the audience that can answer better than me how close it is. But I did tell you this. I can tell you this. I had one graduate student. This is a weird little tangent of my life, which we somehow joined Bell briefly. He did. And we did the 3 pi, E plus E minus to pi plus pi minus pi 0. And we crunched all the way through this, got a beautiful spectrum, could never convince ourselves we had the luminosity normalization enough to publish it other than a thesis. So I agree with you that it's tricky. Why they would all get it wrong, I don't know. And they're going to tell you that the efficiency they have for pion and muon identification is such and such and all that kind of stuff over the angular region and blah, 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 blah. But I'm not in a position to be critical. I'm just saying I know from trying it isn't easy. we just sat there and went, we're not going to publish this because we don't want to throw noise into the spectrum. Yeah, I don't know.
I mean, that luminosity is very well determined from Baba scattering. And so, that whole method has 0.5% is 0.5% is sort of the uncertainty counting B's. But if you're counting E plus E minus to mu plus mu minus or E plus mu minus to E plus E minus, I think we can be better than that.
When you do the ratio.
Yeah.
Yeah, that's the thing. It's the ratio that they bring there.
Right.
And typically, but they have done it both ways. They've done it absolute and with ratio and so on and so forth.
With ratios, a lot of the systematics are dividing out.
Yeah, I would imagine.
All right, I think we should thank Dave again.